So my name's Mitch Schulte. I am a program scientist, a planetary scientist at NASA headquarters in Washington, D.C. And we're here in New Zealand to help people of New Zealand understand about planetary science and what it takes to put together a mission to Mars, either for sending robots, which is what I do. I help send robots to Mars to understand the geology and climate history and all that kind of stuff of Mars, but also what it really takes to get people, hopefully, eventually to Mars. So we're here in New Zealand to talk to the school, to really help them understand planetary science, why NASA is so great, and why everybody in New Zealand should care about space.
And I guess the message is that you don't have to study anything special. You study what you're interested into, and then you can apply it, can't you?
That's right, yeah. So I'm personally a geologist, and so being a geologist helps me understand how the Earth is put together. Earth is a planet too, but what we learn here on Earth helps us understand places like Mars, and I work directly for the Mars exploration program at NASA headquarters, and so bringing what I do to understanding Mars is really something that's just sort of natural for me because of what I've learned, and using what I've learned to apply to things like that.
So I guess you find similar structures on Mars to Earth, isn't it? There's a lot of similarities, I think you said the other night.
Yeah, that's right. So the geology of Earth and Mars are very similar. And so by studying places here on Earth that have similar kinds of features, that helps us really understand what's going on Mars. Yeah. We do see a lot of differences between Earth and Mars as well. And only by studying Mars itself can we really understand the peculiarities of that planet on its own. Yeah. But it also gives us lessons about things that we can take from Mars to understand things here on Earth. So for example, we know that Earth and Mars have very different climate histories. Yeah. So Mars very early in its history lost water at the surface because it lost a lot of its atmosphere. Yeah. And we really understand the reasons for that based on geology of Earth and particularly geology of Mars.
So does it sort of give you lessons of what could go wrong on Earth? Because you mentioned that with Venus on Monday night too, didn't you?
That's right, yeah. So Venus is an example of greenhouse gases gone wild. So the atmosphere on Venus is 90 atmospheres of carbon dioxide, and it's almost pure carbon dioxide atmosphere. Yep. Very, very thick. The reason that carbon dioxide is a problem is because it's very good at trapping heat. So when you build up enough carbon dioxide in the atmosphere, it traps heat that it gets from the sun. And as more and more carbon dioxide builds up, you trap more and more heat. And Venus is a very good example of a planetary scale sort of natural experiment of that process happening. So when we look at Earth and the amount of carbon dioxide we're putting into the atmosphere, we know that that's actually increasing global temperatures, and we also can take lessons from Venus that the effect is real. Yep. And that there are obviously some serious consequences on a global scale for that. The surface temperature of Venus is about 480 degrees Celsius. Yep. And that also means there's no liquid water at the surface of Venus.
The buildup of carbon dioxide.
Yeah, exactly. That's directly related to the amount of carbon dioxide in Venus's atmosphere.
So when people talk about climate change, that's what they're saying, isn't it?
Yeah, exactly right. Yep.
Watch those greenhouse gases.
Yeah, and even on like a laboratory scale, if you took a container and you put carbon dioxide in it, you can actually watch the temperature of the interior of the container rise because it's very good at trapping the heat. Yeah. So, but that's on a small scale, right? And Venus shows us on a very large scale, just like we would see here on Earth, that these sorts of things are real and actually have serious consequences.
So is going back to Mars, is the habitat of Mars sort of similar to a desert situation in New Zealand? Very dry? Or is it quite different?
Nope. Mars is very, very dry. Again, there's no liquid water at the surface. So the temperature pressure condition at the surface of Mars right now is it's very, very cold and there's very, very thin atmosphere. Yeah. And so that combination of factors of temperature and pressure mean that liquid water can't exist at the surface of Mars.
So it's not a desert situation like on Earth then, it's quite different?
It's quite different. Well, it's similar in the sense that there's very little water around, but in a desert on Earth you can actually have liquid water at the surface. On Mars, you just can't have liquid water.
Is that because of the different difference in the atmosphere largely.
Yeah, it's because of the difference in temperature pressure conditions, so that combination. So water at the surface of Mars. Water does exist on Mars, but it's at the surface, it's either in the form of water vapor in the atmosphere or as ice.
So that sort of scenario of the sterilization on Mars, could that happen on Earth?
It's possible. It would probably really take a lot to get Earth to be in dire straits like that. But again, we do take lessons from Mars, and we've actually been studying Mars. We have a spacecraft in orbit around Mars right now that's looking at the rate of escape of gas from the atmosphere. And we think that part of that, that's partly what's responsible for the fact that Mars dried out fairly early in its history.
Okay.
So there was a transition period about 3.5 billion years ago when Mars went from probably being fairly warm and fairly wet, because we see evidence of river channels and lake deposits and all that kind of stuff in really old rocks on Mars.
So that's another example of sort of climate change over a long period of time.
Exactly, yeah. Very different scenario in that case.
To Venus,
Yeah, the atmosphere of Mars has been stripped away by the solar wind.
Okay.
And so and because Mars is smaller than the Earth, it's not able to hold the atmosphere very well.
Okay.
And so it's been stripping it out. Yeah. Yeah. So the solar wind sort of knocks the atmosphere off of the surface, or near the surface of Mars.
So where do you think life will be on Mars if it's there?
So what we're doing at NASA is looking for evidence in the rocks that life existed in the past.
Okay.
Again, because the surface is probably fairly inhospitable to life because of the liquid water problem. I should also clarify that there is some evidence that there may be tiny amounts of liquid water near the surface of Mars, near the surface. If that were the case, though, it would have to be very, very salty water. So like in the wintertime, when you put salt out to melt the ice on the ground to clear up your driveway or whatever, we think a similar kind of thing can be happening, because dissolving salts into water actually depresses the freezing point.
Okay.
And so if you have enough salt in the water, you can depress the freezing point of water enough that you could still get some liquid water. But the result would be that the water would have to be so salty that it would probably not really be habitable.
Yeah.
Not much could really live in it.
Yeah.
So just to clarify that.
So
but
there might have been life in the past on the surface, but there wouldn't be now.
Right, exactly right. Yeah, that's the point. If life could potentially possibly exist on Mars right now, but it would have to be sort of deep underground where there's enough heat to make, and enough pressure to make liquid water.
So I think it was Jen was talking about exploring caves on Mars or something.
Yeah, so exploring caves or the volcanic regions on Mars, which of course would be a nice source of heat. So you could imagine, and we do see lots of places on Earth where there are organisms living in volcanic kinds of environments. And so by extension, if you went deep into a volcano on Mars, there might be things living there, but that's really, really difficult to get to.
Oh, totally. And
yeah.
I think the other one that's been announced recently was that big block of ice, wasn't there?
Right.
It looks like there could be a lake underneath.
Yeah, exactly. Yeah, that's a pretty deep on Mars. Again, deep enough that you have enough pressure to actually stabilize liquid water. But some data from a European Space Agency spacecraft called Mars Express. They have a ground-penetrating radar that actually the reflections in those data look like it's a layer of liquid water. But again, it's pretty deep.
So how hard would it be to find out what's under that ice?
Well, I mean, the only direct way to check is to drill into it. But again,
you've got to get the equipment to Mars.
Yeah. So far we've only been able to drill a few centimeters on the surface of Mars, and so having a drill rig that could go deeper is pretty tough.
So it's not going to be on this 2020 mission.
No. What we are going to do though, what we are going to do though is collect rock samples that'll be about the size of a pencil. So that'll be about as deep as we can go. The European Space Agency is also planning a rover to send in 2020, and they have a drill on the front of their rover that it will go about 2 meters. They won't be collecting samples; they'll just be analyzing them in place. But they'll be able to drill about 2 meters with their drill.
But the ice is thicker than that, is it?
It's much deeper than that. Yeah.
So it'll be a long time until you get the capacity to drill through that.
Yeah, that's right. Yeah.
And you mentioned about the moons as well, down Jupiter and Saturn and and Neptune.
That's right. Yeah. So there's some really interesting places in the elsewhere in the solar system where we think life might have originated. A couple in particular that we're very interested in are moons of Jupiter and Saturn. So Europa is one of the moons, one of the Galilean satellites around Jupiter, and it has about 100-kilometer thick liquid water ocean under the ice crust. And the reason that there's liquid water on Europa is because the gravitational pull of Jupiter as Europa goes around provides enough friction.
It's like
Yeah.
I think Stephen Hawking in one DVD talked about it being like kneading clay.
Yeah, exactly right. Yeah. Yeah, and you get a sense for that if you take a paper clip and you bend it back and forth a bunch of times, and then you feel where the bend point is, it warms up. That's the same kind of thing that's happening. You get this frictional heating.
The gravity gets closer and further away.
It gets tugged as it goes around Jupiter, right? And so it gets pulled as it goes around in orbit around Jupiter. And so that's enough.
Creates a bit of energy.
That creates enough energy to create a liquid water ocean on Europa that's actually 100 kilometers thick.
And I guess that ice is enough to protect what's below.
Yeah. So
from what's happening in space.
Yeah. So the ice shell around it is about anywhere from 5 to 20 kilometers thick. Maybe thinner in certain places and thicker in certain places, but that certainly caps the liquid water ocean and would protect it from a lot of what's going on, because Europa is actually in a really intense radiation environment, because it happens to be where magnetic field lines that are generated by Jupiter actually get concentrated. So the surface of Europa is bombarded with pretty intense radiation. So having something beneath all of that stuff would actually be a little bit more protected. So,
absolutely. And then there was the Saturn moon too, wasn't it?
Yeah. So we had
two Saturn moons, wasn't it?
Well, so yeah, there are two moons of Saturn that are actually pretty interesting. One is called Titan, and Titan is interesting because it has a nitrogen atmosphere like Earth does, and you can't actually see the surface in telescopes or from orbit because a smog layer actually gets created on Titan. Okay. On the surface of Titan, there are lakes of liquid methane. So normally you think of methane as being a gas. It's what you use to, heat your house or cook your food on your stove. On Titan, it's cold enough at the surface of Titan that methane actually exists as a liquid. So there are lakes of liquid methane, and there's a methane cycle, and so methane gets brought up into the atmosphere as a gas. It gets photolyzed by sunlight and turns essentially into smog. And so there's a big orange haze layer in the atmosphere of Titan that's made out of hydrocarbon smog. So that's a really interesting place. The other interesting moon of Saturn is Enceladus. And we had a spacecraft at Saturn until very recently, until September of last year. The Cassini spacecraft, which was in orbit around Saturn for 15, 17 years.
They sent it to crash into Saturn or something, didn't they?
Yeah, and so we actually, it was running out of fuel. And so we didn't actually want the spacecraft to accidentally crash into either Titan or Enceladus, and so we actually directed it to dive into Saturn's atmosphere where it burned up. So that's how we ended the mission. But before the mission ended, it did a number of flybys by this moon Enceladus, and there are some beautiful photographs of liquid water geysers erupting from the south pole of Enceladus. So again, this shows us that there's a liquid water ocean underneath the ice layer on Enceladus.
And that's similar to some sort of thing you'd see at Antarctica, is it?
It's a little bit similar. So in Antarctica you have glaciers, a lot of thick layer of ice, kilometers thick, and underneath them are some lakes. So it's a similar situation from that perspective. So imagine if the ice were to crack above those lakes, you would get, and there's enough pressure in the lake, it would shoot out these geysers of material to the surface. And so this is what we see happening on Enceladus.
So that's what you're sort of comparing, that's your reference point as Antarctica, and seeing, hey, that's similar. There's similarities here, there's something going on here.
Yeah, it's also a little bit similar to like geysers that you find in New Zealand, right? Because in that case it's hot water that erupts because it builds up enough pressure that it shoots out of the ground. Similar kind of thing, but just much colder on Enceladus. So, But enough pressure builds up that it finds its way through the cracks and erupts into space.
And I guess, as you said the other night, that anything, life might be something we don't even recognise or we've got no reference for.
Yeah, that's right. So most of what we do is consider the way life exists here on Earth, because that's what we're familiar with, that's what we know, and we understand it pretty well. But when we go looking in places like Titan, which has methane, liquid methane lakes on the surface, you could imagine that there could be some biochemical reactions that are happening in that, because it's a polar fluid that can carry charges and could serve as some sort of metabolism for some organisms.
Yeah.
But when we try to think about that, it's very far beyond our normal understanding of how life operates, because we're used to life in liquid water at sort of more moderate kinds of temperatures. But you could imagine that things could technically be alive in systems like that on Titan. But we really have to think about all the things that we know in terms of the chemistry and physics that make up life and apply that to a situation like that. So it's not out of the realm of possibility, but it's something that's kind of far outside of our normal experience.
Almost science fiction, isn't it?
Yeah, in a lot of ways.
Science
That's right. Yeah. That's right. Well, and a lot of science has started as science fiction. So, having cell phones and that kind of stuff started as somebody's idea that, hey, wouldn't this be a really cool thing?
I guess science fiction is really the sort of the scientists or the engineers testing out their theories, isn't it?
In a lot of ways. I mean, it's people dreaming, right? And thinking what could possibly be. Again, so things like traveling at warp speed, like in Star Trek, is probably not possible, because there are certain rules of the universe that you can't break, like traveling faster than the speed of light. But the idea that you could have something without wires that you can carry around with you, that you can use to communicate across the planet, is something somebody dreamed up, but at the time there was no reason to think that was real. And here we are, everyone having a cell phone.
Well, I think that's what Stephen Hawking said in the DVD series of his. He said that when he trained at university, it was, if you talked about life somewhat outside of Earth, you'd be considered mad.
That's right, yeah.
But now it's quite normal to
and again,
beyond Earth, isn't it?
and so part of that is, the more that you explore things, the more you learn. And as we've discovered over the past 100 years that scientists have been looking at microbiology and understanding how DNA works and all that kind of stuff, we have found life in so many various environments that we never thought life would have existed in before. And as an example, there are these geysers on the seafloor that are called deep sea hydrothermal vents. And they're not only great places for microorganisms to live, taking advantage of the volcanic gases and the temperatures that exist in these systems, but there are these huge communities of animals that are down there feeding on these microorganisms. And we did not even know that these things existed until 1977.
Incredible, isn't it?
So it was,
it's the extremes, isn't it?
Yep. It was only 40 years ago that we found these things. And now, this has given rise to, okay, well, if something can live down there, then maybe it's not crazy to think that something could live at the bottom of the ocean on Europa.
Oh, exactly. And I guess further afield than that, isn't it? If planets like the one at, Proxima Centauri, that's in the Goldilocks zone.
Sure, yeah.
It's perfectly plausible that there could be life similar to Earth, isn't there?
And of course, we've been finding thousands and thousands and thousands of exoplanets now, planets orbiting around stars outside of our solar system, still within our galaxy, because that's as far as we can sort of get those data. But everywhere you look in the sky, and we've only studied a very, very small part of the sky, but already we've found thousands of planets circling other stars. And just with the sheer number of planets out there, there probably could be life on some of them.
It's 100 or 200 billion stars in the galaxy, isn't
there?
Yeah,
yep, exactly right.
There's got to be billions of planets, isn't there?
Right, yep. So it's, just you
if
do the
it's
math
only
and, right.
0 something % of
exactly,
possibility of life.
That's right, yeah.
there's still there's potentially a lot of examples out there, isn't there?
That's right,
it's
yeah.
just a matter of whether we can find them or not.
And it gives us hope that, we're not crazy, that we're actually doing something that might pay off in the end. And, again, we're learning a lot about various places. And the other thing I want to point out about that is you mentioned the term Goldilocks zone.
Yeah.
Technically, Europa is outside the Goldilocks zone.
That's right.
Right? Because it's far enough away from the sun that the surface of Europa or Jupiter wouldn't be a place where you'd want to live or could live. But if you had a particular environment that allowed you to have conditions where there's liquid water and other kinds of things that we think life needs, then, we've expanded our definition of what the habitable zone is a little bit, I think.
Exactly, yeah. So are we going to find life away from Earth in our lifetime?
That's a good question. We get asked that all the time. I don't want to say definitively yes, because it is a hard thing to do. We know of one example so far, and that's Earth. We are looking at Mars. Again, if you want to be able to drill into Mars where you might find life that's alive right now, that's a lot of technology we have to build. That's a lot of money we would have to spend to be able to go there and do that.
Exactly.
And at the moment, it's just really not that technically feasible. So what NASA concentrates on for Mars now is looking for, again, evidence in the rock record, like we see in ancient rocks on Earth,
Yep.
that life left behind a footprint, as it were.
So that's what you're really looking for on Mars at the moment.
Yeah, exactly right, yeah. And so we
you're
do...
looking for the habitability rather than necessarily finding life itself.
Yeah, exactly right, yeah. Because if you don't find things that are living, that are really, really old, but we see evidence in the rocks on Earth. A great place is Western Australia, just across the Tasman Sea there, where you see evidence left behind in the rocks that life was once there. And that's what we're looking for on Mars. So we're hoping to go to a really old terrain, interrogate some rocks that might contain evidence, we call them biosignatures, that life might have left behind.
That's another familiar term from science.
There you go.
Biosignature.
Yep, exactly, yep. And so for something like Europa, we actually are planning a mission to study Europa more intensely. Again, getting through 10 kilometers of ice. We're just not anywhere close to being there at the moment, but we need information, right? And so we need to study Europa more intensely. So we're planning a mission to go out there now. It's going to go into orbit around Jupiter and make 45 close flybys of Europa. Okay. So we can get a lot more information about, the thickness of the ice, the nature of the ocean underneath it, and, sort of study the surface and study the moon in a more intense way than we've been able to do before.
That's pretty good. That's